Kimi K3 has almost 3 trillion parameters. That is an absurd number. It is one of the largest open-weight AI models ever built, far too large for a normal computer and large enough that simply moving its data between GPUs becomes a serious engineering problem. But here is the strange part. When Kimi K3 processes a token, it ignores more than 98% of its experts. Only a tiny part of the model actually wakes up. And that is not a weakness. It is the reason the model can work at this scale. Because Kimi K3 is not really a story about building the largest possible neural network. It is a story about building an enormous network and then carefully deciding which parts to use. So, how can a model contain 2.8 trillion parameters, support extremely long contexts, and still generate tokens efficiently? The answer comes down to 4 ideas: mixture of experts, stable latent MoE, Kimi Delta Attention, and attention residuals. Together, they solve 4 different problems: computation, communication, memory, and information flow. A 3 trillion parameter model is too expensive. Imagine that every time you entered a prompt, Kimi K3 had to activate all 2.8 trillion parameters. Every layer, every weight, every calculation. Even on powerful data center hardware, that would be painfully expensive. So Kimi K3 uses a technique called mixture of experts. Instead of treating the model as one giant block, it divides part of the network into many smaller components called experts. Different experts learn different internal patterns. Some may become useful for code. Others may respond more strongly to mathematics, language, planning, visual structures, or other patterns that are difficult to name directly. Kimi K3 contains 896 experts, but for each token, it activates only 16. That is roughly 1.8% of the expert pool. Think of it like a company with 896 departments. When a task arrives, it does not call every employee into the meeting. A routing system selects the 16 departments most likely to help. The company can contain an enormous amount of knowledge without paying the cost of using everyone for every decision. This is the central trick behind Kimi K3. Its total capacity is enormous. Its active computation is much smaller. But dividing a model into hundreds of experts creates another problem. Those experts do not all live in the same place. The experts are spread across GPUs. A model this large cannot fit on one GPU. Its weights have to be distributed across many accelerators inside a data center. Some experts may live on one GPU. Other experts may live somewhere else in the rack. When the router selects experts for a token, the token's representation may need to travel between multiple GPUs. And moving data is not free. GPUs are extremely fast when calculating with data they already have. But when information constantly moves across chips, communication can become the bottleneck. You may save computation inside the model, only to lose that advantage while transferring data. Kimi K3 addresses this with stable latent MoE. Before a token is sent to the selected experts, its representation is compressed into a smaller latent form. Instead of transferring the complete high-dimensional representation, the system sends a compact version. The experts process that smaller representation, and the result is later expanded back to the model's original dimension. It is like sending a compressed project file instead of transferring a folder containing every raw asset. Less information has to travel between GPUs, reducing both communication and computation. But the word stable matters too. Choosing the right experts. Every token needs a router to decide which experts should process it. With 896 experts and only 16 available slots, tiny changes in routing scores can have large consequences. A few experts might receive too many tokens. Others might barely be used. That creates load imbalance. Some GPUs become overloaded while others sit underused. Kimi K3 uses a technique called quantile balancing to make this process more stable. Instead of judging experts only by their raw routing scores, the system considers where each score sits within the broader distribution. Imagine comparing students from different exams. A raw score may not tell you everything. Knowing that a student ranked near the top of the group gives you more useful context. Quantile balancing applies a similar idea to expert routing. It helps the router compare experts relative to the rest of the pool, making selection more stable and distributing tokens more evenly. So stable latent MoE does 2 things. It reduces how much data moves between GPUs, and it helps ensure that hundreds of experts are used more effectively. But experts are not the only expensive part of a transformer. The next problem appears when the context window becomes extremely large. Attention gets expensive. Attention allows a transformer to connect one token with other tokens in the context. It is how a model connects a variable to code written hundreds of lines earlier. It is how it follows references across a document or remembers instructions from the beginning of a conversation. But traditional attention becomes increasingly expensive as the context grows. When the number of tokens doubles, the work can grow much faster than double because the model calculates relationships between many token pairs. For short prompts, this is manageable. For hundreds of thousands or around a million tokens, it becomes a major bottleneck. Users want models that can inspect an entire codebase, read long reports, or follow an agent working for hours. But the larger the context becomes, the more expensive conventional attention is to run. Kimi K3 approaches this problem with Kimi Delta Attention, or KDA. Instead of using full global attention in every layer, Kimi K3 uses a hybrid structure. Most layers use Kimi Delta Attention. Periodically, a global attention layer is added so the model can reconnect information across the entire context. The architecture uses roughly 3 KDA layers for every one global attention layer. KDA handles most token processing efficiently. Global attention preserves the ability to retrieve information from distant parts of the context, a more efficient kind of memory. A useful way to understand KDA is to imagine that the model maintains a compact memory state. As new tokens arrive, it does not compare every token against every previous token from scratch. Instead, it updates that memory. New information can be written into the state. Older information can gradually fade. Important patterns can remain available without storing every possible relationship explicitly. But this creates a difficult question. What should the model keep? What should it forget? And how quickly should different kinds of information disappear? A temporary formatting detail may only matter briefly. A user instruction, function definition, or important fact may need to survive much longer. Kimi Delta Attention gives the model more precise control over how information is retained and forgotten across different internal channels. Some channels can update quickly, others can remain stable for longer. That creates a more flexible memory system than applying the same forgetting rule to everything. Because the model relies heavily on this compact evolving state, decoding can remain much faster in very long contexts. Moonshot reports several times higher decoding throughput in long sequences compared with relying entirely on conventional attention. Full attention has not disappeared. The global attention layers still act like synchronization points. KDA carries information forward efficiently, while occasional global attention allows the model to search broadly across the context. It is a hybrid between transformer-style attention and recurrent memory. Global attention is valuable. Kimi K3 simply avoids paying for it in every layer. Deep models can lose information. Even with efficient experts and attention, another problem remains. As information passes through hundreds of transformations, useful details from earlier layers can become diluted. Transformers normally use residual connections to reduce this problem. A residual connection allows information to bypass a transformation and continue forward. Instead of completely replacing the previous representation, each layer adds its changes on top. But in a very deep model, a standard residual stream still has limitations. A late layer mainly receives the accumulated result of everything before it. It cannot easily choose a specific earlier state that contains the information it needs. Kimi K3 uses attention residuals to make this flow more selective. Later layers can retrieve information from earlier residual states instead of relying only on the immediately previous representation. It is like editing a document while still being able to reopen important earlier drafts. The model does not need to accept one long chain of increasingly modified information. It can selectively bring useful signals forward. Connecting every layer to every previous layer would be expensive, so the architecture groups layers into larger logical blocks. This gives the model access to earlier information without creating an uncontrollable number of connections. And once again, the same design philosophy appears. Kimi K3 gives the model more choice, but places limits around that choice. It has 896 experts, but activates 16. It supports global attention, but does not use it everywhere. It can retrieve earlier residual states, but does so through organized blocks. The model is enormous, but its architecture is built around restraint. The bigger picture. The most interesting thing about Kimi K3 is not its parameter count. A larger model is not automatically a better model. If every parameter participates in every token, size becomes a burden. If experts are distributed across GPUs without efficient communication, sparsity loses its advantage. If long context requires global attention everywhere, inference becomes too slow. And if information disappears across deep layers, additional depth becomes less useful. Kimi K3 attacks each bottleneck separately. Mixture of experts reduces active computation. Stable latent. MoE reduces communication and stabilizes routing. Kimi Delta. Attention makes long context processing more practical. Attention residuals improve how information moves through a deep network. The real achievement is not any one of these ideas, it is how they work together. The experts make the model sparse. The latent representation makes that sparsity practical across GPUs. The hybrid attention system reduces the cost of long sequences, and the residual system prevents information from disappearing inside the model's depth. So yes, Kimi K3 is a 2.8 trillion parameter model. But that number is almost misleading. Its real identity is not a model that uses 3 trillion parameters at once. It is a model that has access to 3 trillion parameters and has learned when not to use them. That may be the more important direction for AI scaling, not activating everything, not remembering everything in the same way, not connecting every layer to every other layer, but making better decisions about which computation, memory, and information paths matter right now. The future of AI may still involve larger models, but Kimi K3 suggests that scale alone is not enough. What matters is selective scale, a huge model, a small active path, and an architecture designed to make every activated part count.